Good morning. We'll continue discussing about the probability distributions. An important distribution in the field of statistics as well as data analysis is a probability distribution called as normal probability distribution. So why it is called as normal? So we'll look into that. This was given by the famous mathematician called as Gauss, and hence it is also called as Gaussian distribution after him. Now coming to the word normal, most of the distributions or the variables what we observe in the nature, they normally tend to behave with respect to this distribution. So that's why they have given the name normal distribution. Now how is this normal distribution defined? And as said, it is a continuous distribution. It is not defined for discrete values. Even if your x is discrete, in a long run, that is when you consider large number of values for that particular discrete variable, then that can be treated as a normal distribution. So we have a continuous variable x, like say age of a student or blood pressure of a patient, weight of a newborn baby. So that continuous variable, if I want to say that it follows normal distribution, then it should follow a particular probability law, and that law is given by f of x is equal to 1 by sigma square root of 2 pi into e power minus half into x minus mu divided by sigma whole square, with x taking the values minus infinity to infinity. Mu also takes the value minus infinity to infinity. Sigma is greater than 0. Mu and sigma are two parameters of the distribution. So we'll look into this each and every term here. So first of all, if you remember, we use the notation P of x is equal to probability that x takes a particular value of x, and if it is binomial, I said that is NCX e power e to the power of x q to the power of n minus x. And similarly for Poisson, we said that it is e power minus lambda power x by x factorial. And here x was taking discrete values. In the first case it is 0 to n, in the second case it is 0 to infinity. Now here, since x is discrete, I can observe each and every individual value of x so that individual probabilities can be obtained. But when it comes to a continuous variable, exactly telling that that variable will be equal to that has a less chance. Therefore, we say for continuous variables, we cannot write p of x is equal to x. And statistically, even if you forcefully try to obtain that, that will come out to be exactly equal to 0. Because the variable is continuous, it doesn't take any specific discrete values. It takes the values in a range. So if I say my height of say students are in between the values 10 and 50 kgs, so it could be any number between 10 and 50, and even for shorter cases we may consider the sub ranges like say 10 to 15, 15 to 20. So the values are taken over small ranges but not individually. So for every continuous distribution, we can't write p of x is equal to x. So we'll write it as a mathematical function fx, or you could call it as px also. That is not fine. But we are not talking about the discrete values of x. Now coming to the right hand side of the law, it is some mathematical function 1 by sigma square root of 2 pi e power minus half x minus mu by sigma whole square. So here my variable x is observed here. Its mean is indicated by mu and its variance is indicated by sigma square. So we have a variable. So whenever we have a variable, we can obtain its mean, we can obtain its variance. And if that variable is following the probability law given by this function, then we say that the variable follows normal distribution. And we have learned so many techniques of verifying whether a particular variable follows normal distribution. So first case, you obtain the possible values of x, you create class interval and frequencies for shorter ranges of x, plot the histogram and see what is the shape of the histogram. If it comes out to be a symmetric curve or a curve, a polygon is such that it is close to that, in that case, we can say that the distribution is normal. And second way is you can actually obtain the quantile plot in order to verify that. And third category, you can verify some of the properties of the normal distribution itself. So when it comes to the examination point of view, so here you are supposed to learn this. And for any continuous distribution function, the probability density function or the f of x probability law is called as PDF, which simply gets expanded as probability density function. So in the case of discrete variables, we call it as PMF, probability mass function, because mass of every, probabilities are mass for every particular values of x. So here we don't talk about particular value of probability. We talk about the area between two particular values of x. Therefore, this is called as probability density function. Okay, so let us look into the shape of this particular density function. So what I do now is I'll take an exercise and I'll show you how the plot comes. To make the things very much simpler, I take mu is equal to 0 and sigma is equal to 1. In that case, so I could have, right, so a special case where my variable x is such that its mean is equal to 0, its standard deviation is equal to 1. So I could observe many such variables in the nature. So if that happens, then in place of sigma, you will have 1. In place of mu, it is 0. So the density simply takes the form 1 by square root of 2 pi e power minus x square by 2. So these are the two parameters. Parameters are the constants observed in the probability function, which is statistically called as the distribution or population. So you have an x, its population follows this rule. So you pick any number of any value, particular value of x from this, and that you will call as an observed sample. So basically you have the weights of patients, they follow normal distribution. If you randomly select 10 patients and extract their weight values, those are said to be the sample values obtained from this particular population, provided weight follow normal distribution. And in most of the cases, weights of any particular item, people, newborn babies, they have a tendency to follow normal distribution. Now coming to the range, in case of binomial and Bernoulli as well as in Poisson, we said x takes discrete values like 0, 1 or 0, 1 to n or 0, 1 to infinity. So here x takes any possible number between minus infinity as well as plus infinity. So I could have this x taking minus 25, I could have x taking 0, minus 3.5, 1.6, 18,000, etc. So I could have variables which takes very possible extreme values, but when you look into a particular characteristic, you will rarely observe the presence of extreme values. Now, since x takes negative as well as positive values, and when we look into the mean, mean is the measure which is based on all possible values of x. Therefore, mean also behaves similarly to that of x. Therefore, your mean could also be negative as well as positive. So it also takes the range as minus infinity to infinity. And the second parameter is sigma. Sigma indicates the standard deviation and sigma square is the variance. And by the property of variance and sigma standard deviation, we know that variance is always greater than 0. Standard deviation is always greater than 0. So you can take this. So pick some x values to be negative, compute the mean, compute the standard deviation. You will observe that if you have many negative values in the x, your mean turns out to be negative, but your standard deviation will be always positive, whether you have negative values or positive values in your x. Now let us look into the frequency polygon of this particular distribution. So to make the thing simple, I have taken this particular density. So we'll see how the curve for this distribution, this x comes, and then we will see what happens to the more particular particular case when we have special particular values for mu and sigma, and then from this we could always try to obtain a simple form called like this by doing some transformation such that my variable always produces mean 0, always produces standard deviation 1, and we'll see why that is important in the field of statistics. Now just for the sake of understanding, I'll be doing this, so you may not worry much. So as said, what I'll do is I'll define some x values, and as said, x takes many such possible values from minus infinity to infinity. So I'll not take all such possible values. So let me start it from say 5, and I cannot say 4. Okay, so 4, 3.99, 3.98, and since x takes minus values also, so I'll start the values from -4, and I'll select the values with an interval 0.01. So basically I'm defining a variable which is taking the values from -4 to +4, and there are infinitely many possible values from -4 to +4, but I'm selecting only some specific values with an interval 0.01. So I'll produce this. So when you look into the mean of that variable, you will see that to be equal to 0, and variance is equal to 1. Just give me a minute here. So have produced some x values from -4 to +4. So you could ask question, why -4 to +4? Could take -10 to +10, -6 to +6, any number. But what we observe now is,
Your screen is not visible to us.
sorry. Okay. So I have the values of x in the first column. So I've selected from -4 to +4. You could take -100 to +100, but since it becomes very large in number, so I'll just stick to this. And later when we see the particular reason why I selected -4 or a number close to 3. Now I define this f of x. So it is 1 by square root of 2 pi into e power minus x square by 2. So I'll use the built-in function exponential to the power of minus x square. So I need not worry about these things. Just I'm generating the graph of the normal distance. Okay? By square root of 2 pi. I'll obtain this for each and every case. So I have x, I have f of x, which is obtained from the normal density. Now I try to obtain the graph of that. Okay. So if you look into the shape now, so you're getting a perfect symmetric distribution. And if you look into the shape of the peak of the curve, it is neither very sharp nor too flat. And if you look into the middle value, as said, it is 0. Therefore, the mean, median, and mode for the distribution is 0. And if you look into the values of f of x, see, When I have x as minus 4, the density is producing value 0.0014, which is a number closer to 0, and it gradually increases as my x value also increases. So this exercise is helping us to understand the shape of the curve. Now you can produce it for minus 3 to 3, minus 2 to plus 2, or if you want to really have large cases, you can pick minus 100 to 100. But whatever the value you take, you will observe that in most of the cases, till your x reaches 3, the tail will be very much close to 0 only. So if you take minus 4, minus 5, minus 6, minus 100 to 100, this always, takes the value closer and closer to 0, and you will observe the curve actually from, say, close to minus 3. So if you are observing this point, so this is the point where your curve is actually changing the shape. Now, if you extend this to minus infinity and plus infinity, it will follow the line y is equal to 0 on either side. So, if you pick any such variable for a normal curve, you are observing that the values start from minus 3. And though you could say I have taken only x from minus 4 to plus 4, what if you have x as a different set of variable and mu is something, sigma is something? Now to answer that question, so I'll take you to next exercise. Here, what I have is I have three different variables. So first I have taken x1, which is weights in kgs. So I have randomly observed some 11 or 12 patients' weight here. So they are recorded in kgs. And for that values, I have computed mean and standard deviation. And in the very first row, mu1 indicates mean of x1, and I have sigma 1, which is standard deviation. Now, since unit of measurement is carried by the measure, so both mean and standard deviation will have the same unit kgs. Next, I have recorded another variable, maybe height of certain number of students. So I have recorded the height values in centimeters. Therefore, I have this. Now we priorly assume that these values follow normal distribution, and now see whether my assumption is true or false. Next, as said, even if you have a discrete variable, like say your count values like number of decayed tooth, number of accidents, number of births, when you look into the large possible case. So here I have taken only some 11 values, I guess. So even if you look into say 20, 30, 40 values, or as small as this, I could say asymptotically it follows normal distribution. So just to check whether it happens, I have selected some random values, and again for that I have computed the mean and standard deviation. Now if you look into the function said e power minus x1 minus mu1 by sigma 1. So our variable is defined in the function such that it is x minus mu divided by sigma. So let me see what happens to this x if I subtract every value of x from its own mean and divide that difference by standard deviation. Now, standard deviation is 12.3256. So you observe this. So your z values are C minus 0.7, minus 0.2, 1.5, minus 1.60, etc. So even if by chance there is a presence of extreme value, say you have recorded 0, see, you will observe z to be only minus 4.5, which is maximum. So if you have an 100, it is 3.57. So what we are observing is, so I have my x taking any particular value, of course, within that particular range of the variable. But when you look into the converted variable, which we indicate as z, why z? Well, look into that now theoretically. Your z mostly lies between minus 4 and plus 4. So even this minus 4 plus 4 are very rare. But to be precise, I could say it lies between minus 3 and plus 3. I can check this for this variable also. So I have the heights here. What I do, I'll subtract every height from its mean. Mean is 7.47. and I'll divide the difference by its standard deviation 19.3. So you can see that my again values are well within range -4 plus 4 or -3 plus 3. So even if you have a rare case where the person is very tall or the person is, let's say, very short, even in that cases, your Z doesn't go beyond that particular range. So naturally occurring variables, most of the cases, they tend to follow this particular law. Now let us see what happens to a discrete case like this. ದಯವಿಟ್ಟು ಮ್ಯೂಟ್ ಮಾಡ್ಕೊಳ್ಳಿ, ಯಾರು ಮ್ಯೂಟ್ ಮಾಡ್ಕೊಂಡಿಲ್ಲ. Okay. See, so even in this case, you're observing this. So that is the reason why in the previous exercise, I took values from -4 to +4 and I called it as x. Now the same x in this particular example is indicated in terms of z. So whether it is x or z, it is following normal. So if you have a different value of x for which you have mu non-zero, sigma non-1, in that case, you can generate a normal distribution by defining z is equal to x minus mu1 by sigma. And if you look into this z, it is same for all x. So whether your x is in kgs, whether your x is in centimeters, whether your x is defectives or any other variable, once you convert that x into z, where z is defined as x minus mu by sigma, your z is same. And if you look into the unit of z, there is no unit. See, in the first case, I had x as kgs. So x kgs minus mu kgs divided by sigma kgs, the kg get cancelled. So your z is a unit free measure. Even in this case, z is a unit free measure. Even in this case, z is a unit free measure. So you can produce or you can convert a particular x into a same z. Now, since I have practically observed that my z only takes values, from -3 to +3. So only in the sense, in most of the situations this happens, but theoretically speaking, we say it takes values from -infinity to +infinity. But those cases are very hard to observe. What we most frequently observe is values coming between -3 and +3. Therefore, the properties of the distribution could be easily studied if you have this distribution, which is defined only between -3 and +3 practical cases, and the shape looks like this. Its mean is 0, its standard deviation is 1, and that distribution, which is the product of our normal distribution, is called as standard normal distribution. Okay, so we have looked into the shape. So whether it is any such particular distribution for x, you can see that the shape of x can be reduced into this form by converting into z. And if we work back and look into all such possible values of x from -infinity to infinity, so you record height values, pick some 100 height values, and use the law f of x is equal to 1 by sigma root 2 pi e power minus x minus mu by sigma whole square, where mu and sigma are the mean and standard deviation of this, and do a simple exercise. Instead of taking this function, you will observe that it produces the same curve. Therefore, this curve is most frequently or commonly called as bell curve or bell-shaped curve, because the shape matches very much with that of a bell, and this is called as the normal probability curve or the curve of the normal distribution, normal density curve, etc. So when I say I'm talking about an x which is normal, the middle value will be mu, and I could have x value taking anything from -infinity to infinity, and your curve doesn't go to the negative part of x. The extremes meet 0 at -infinity and +infinity. And if you look into this now, so since it is a continuous curve, you can't produce the probabilities. You can't say what happens to a particular value of x. So if I say x is equal to 5.4, what is the probability of x is equal to 5.4? As said earlier, you can't pick the particular cases, but you can say what is the probability that x is in between 5.4 and 5.5, or what is the probability that my x is greater than 10. What is the probability that x is less than minus 3? So only for ranges of values like x, like this, we can obtain the probabilities. And theoretically speaking, if you are obtaining probability for any such range, that will be same as the area. So whatever the area you observe under the normal curve from this value, say 5.4 to 5.5, thus itself is area. Now the question is how to obtain this area or probability. As said, if you have your x which follows normal distribution with mean mu and some deviation sigma, you can always convert that into z, which is defined as x minus mu by sigma. That is also normal, but its mean is 0, standard deviation is 1. And this, in most of the practical cases, takes values between minus 3 plus 3, but theoretically the range is again in between minus infinity and infinity only. But we have, reduced the span of the possible into a very small scale. Therefore, for each and every particular value with a skip of 0.1 or 0.2, we could produce the area, and those areas are recorded, and they are in the form of what called as normal tables or standard normal tables. So what is the standard normal tables? So this Z is called as standard normal variable, standard normal variable, and the process of reducing your x into z, process of reducing x into z by defining z is equal to x minus mu by sigma is called as standardization. Now the first step in computing area or probability for any x is reducing the values of x into z, and our, as known as said, z always lies in between this. So for most of the possible values from minus 3 to plus 3 or minus 4 to plus 4, we have computed the areas, and those areas are recorded, and they are called as normal probability tables or the areas, and they are available, and one can easily use these tables in generating the probabilities. So as said, most of the values are from minus 4 to plus 4 or minus 3 to plus 3. So here this particular table is producing the value from x is equal to minus 3.5, and it gives you the values at say if you want the second digit, it is given in the very first row. So this 0.9998 is the probability value from 3.5, and if you look into the definition, there are several ways to define normal tables, and different possible tables are there. One must always see what is the definition of that particular table. So here it is telling that it is giving you the area under the normal curve from z to infinity. So if I pick any particular z, the number inside the table, inside that is the body of the table, it is producing the area from that point up to infinity, from that point up to infinity. That is, if you want to mark the value minus 3.3 in the curve, and if you have a question, what is the probability that the area of the curve from minus 0.33 to infinity is, that is given by that table. So no need to do any manual calculations for the computation of probability. The only calculations involved are converting our x into z. So as said, now you are interested in obtaining a particular probability. Say have x, it follows normal distribution. So let me take that particular exercise example what I just gave. So I had heights So I had X as weight. This was the first example I had taken. I had recorded mu as 55.89 and sigma was observed to be 12.33. So now you could have a question. What is the chance that, so if you have observed this, so I have recorded the weights, or you are interested in the weight value, and we have observed the values are like this. These are the values for a sample. So let me say that my population is such that on an average, my patients are close to 60 kgs and their standard deviation of weight is about 10 kgs. So this is some hypothetical value. I have assumed this. Now, every assumption in the statistics has to be proved. So we'll see whether this assumed value is a true value or false value. That will look into the later part. This is the scenario. So I have hypothesized that the weight of the patients who are healthy and who belong to a particular age group, their weight is 60 kgs on an average with the standard deviation of 10. Now, if I say, if this is the situation, then what is the chance that if I expect a patient, his weight is exactly in between 55 and 58? Or what is the chance that I will observe a patient whose height is more than 60? Now you have question that, can I observe a patient whose weight is really below 25? So you could have such questions, and the normal distribution gives you answer for that case. So I said first step is reducing the values of x into mu and then looking into the value of z. Now let us understand the z table first. So this is your normal table z. So when I say I'm talking about the distribution z, middle value is 0 because that is the mean of z, and I have the extreme values as minus infinity to infinity. Now, if you want a particular probability in z, say if I want what is the probability that my z takes value greater than 3.3, what is the probability that z is in between 1 and 2? What is the probability that my z is above minus 2.5? So this could be easily obtained by the table, and let me show how this works with respect to the curve as well as table. I have minus infinity, 0, infinity. So I'm talking about a case where z is greater than 3.3. So 3.3 naturally comes after 0. So mark this 3.3 here. Now when I say greater than 3.3, I mean from 3.3 up to all possible values. So this is same as area from 3.3 to infinity. Now use a normal table which produces values from z to infinity, and that is what the tables we have here. So this is giving you answer from a particular z up to infinity. See, read the title, area under the normal curve from z to infinity. Now my z I'm interested here is 3.3. So see where you have z 3.3 in the table. So these are all negative values. So scroll the table to observe the positive values of z. So I said it is generated from minus 3 to plus 3. So I get 0, 1, 2, so on. And then I have 3. So there is no 3.3 here. But if you look into the probabilities actually, as you reach the values 2.6 or 2.7, 2.8, 2.9, your probabilities are becoming more closer and closer to 0. See, it is 2.9. This value is 2.99. So area from 2.99 to infinity is 0.00. And then for various cases of 3, 3.1, 3.2, and if you look into the last value, this is the answer for the probability above 3.9. So just after reaching the value 3.09, you are observing no tail at all. So what I mean is, so you're talking about a situation where you have your x as say minus 3.3. Now really, if you actually look into the normal curve, minus 3.3 is there. And what is the area there? So your tail is actually lying on that particular value, which is nothing but our infinity. So 3 ಗೆ ನಿಮ್ಮ tail 0 ಬಂದ್ಬಿಟ್ಟಿದೆ. So there is no area there. So any area above 3.3 means that is equal to 0 because there is nothing left. So just you observe your curve reaching minus 3, the curve touches your x-axis, not theoretically but practically. Therefore, we say there is no area left. Therefore, we say it is 0. So that's why the tables are such that they give you values only from minus 3 to plus 3. And if you need any value, above plus 3 or below minus 3, we'll consider that to be a number practically close to minus infinity. And those areas are taken to be 0. Now coming to the question, so if you want answer for any other number which is not 3.3, so let me say you need an answer for z greater than 1.5, then mark 1.5 and see what is the area from 1.5 to infinity. Now you have the value 1.5 here. So as said, it gives you various cases from 1.5. So this is 1.50. This is for 1.51, 1.52, and so on. My value is 1.5, which is 1.50. So this area from 1.5 to infinity, so that is equal to 0. So I have 0.668. This is the probability. Now using the same table, you can easily produce the probabilities in between 1 to 2, greater than a number, less than a number, and so on. So if I say I need 1 to 2, so mark that value 1 to 2. So you need this particular chunk of area, but your table gives you an answer. If I pick a value at 1, that means it is producing area from 1 to infinity. If you pick a value at 2, that means your table is producing area from 2 to infinity. Now you need an answer for this case, which is between 1 to 2, but your table is producing 1 to infinity and 2 to infinity. So from this, if you subtract this 1 to infinity minus 2 to infinity, that will produce area 1 to 2. So see the table at 1, you will see the table at 2, and you will subtract. Now if you look into the table value at 1, so you have 0.1587, and table value at 2 is 0.08. So table value at 1 is 0.1587, table value at 2 is 0.0228. Obtain the difference of those two numbers, that is our area between 1 and 2. Now this is how we read the standard normal tables. So since it is new, it will be difficult for you to read and understand the table. So this is a part of second PUC textbook, and at the end of the textbook you can observe the normal probability tables. So please join back again.